Hello everyone. Today I would like to show you the precise prefix-cache-aware routing mechanism in llm-d, and the whole implementation is inspired by this blog post that tells the prefix caching in vLLM to the distributed scheduling with llm-d. Now, the topics that we'll cover is the problem statement, why the standard load balancing fails for LLM-based inference workloads. We will also see the prefix-cache-aware routing, and we will see the difference between approximate versus precise and how they work. And I'll show you the deployment setup that I have, and I'll show you a precise routing in action. And also I'll show some observability and results and takeaways from the implementation. So the problem statement, first of all, for a round-robin fashion traditional load balancing setup, LLM inference workload doesn't work that way because of the fact, say for example, there are two requests coming in, and the first request comes in to pod A, and it computes a KV cache, and KV cache is the most expensive computation memory-bound implementation. Memory in the prefill stage as well as in decode phase, the attention mechanism computes KV cache for every token, and it needs to then pull that from the KV cache to reuse it. So basically, during that computation, say for example, if the request has the KV cache computed for the first request, the second request will have a lot of similarity in the context that it's actually sending, and still recomputes if it goes to the part B based on the round robin mechanism. It's say for example, for RAG context or agentic based implementation, there is a lot of system prompt and the context that will be sent across, which are same across multiple requests. So it doesn't require recomputation because it's wastage of compute, which is the most expensive utility at this point, and it's much more expensive in terms of computation cycle, in terms of performance, from a latency standpoint, and from a throughput standpoint. So for all these reasons, it's always important that we have a different routing mechanism, which is much more intelligent than just round robin mechanism. Now, think about this in thousands of range, if not millions, right? There is thousands of requests that comes every minute and needs to be computed, so it aggregates and adds up fast. Now, what is being offered by vLLM? vLLM provides this automatic prefix caching APC. What this does is it stores the KV blocks in GPU memory indexed by the token hash. So when the same prefix comes again, it reuse the cache blocks again and skip the compute again. So this reduces the TTFD, time to first token, and then basically helps us use the KV cache and not recompute back. But the problem arises when it comes to the distributed computing. The real world scenarios for enterprises is we'll have multiple parts, multiple instances of the LLM workloads and different GPU workloads, right? So llm-d offers a solution in terms of prefix-cache-aware routing. And one of the component is EPP, endpoint picker, which extends the APC across parts, the automatic prefix caching. So which provides it's a gateway extension, Kubernetes implementation that extends the gateway API, and it knows which prefix blocks are cached on which pod. And this basically enables the routing mechanism to score and send the request to the pod which the best cache match is. Now, there are two mechanisms, precise and approximate. Approximate is when looking into the history index inside EPP and send the request to whichever pod it was previously sent. But then precise is much more, the prediction is usually correct in approximate, but then precise is much more based on the fact, because the KV cache or the KV events are being sent from the pods into the EPP, and the EPP polls it and indexes it, and based on different scoring mechanisms, it makes the decision and provides a weight to see which pod the request has to be routed. And it requires a tokenizer sidecar, 0MQ for event streaming, and then the KV events config needs to be set up in such a way that all the pods has to be streamed the KV events into the EPP or the scheduler. So what has been seen by the llm-d's test cases is the benchmarking on it is it's 57x faster TTFT than approximate and 2x throughput versus random. Now, EPP multi-signal scoring. So there is a scorer implementation. The major architectural diagram for the scheduler is up here. So it's basically have the vLLM fleet sending the KV events to the KV events pool, and that will be updating the index into the KV block index, and then the scheduler, inference scheduler, which is also the EPP, will be pulling this when the request comes in and take the KV cache indexer and do a decider. The decider decides it to give the weightage and based on the KV blocks index. Now, you can provide score for different scorer mechanisms here. So this is one precise prefix cache scorer, and then there is KV cache utilization scorer and Q scorer. So you can look into the Q depth, you can look into the KV cache utilization on that particular pod, and you can also see how much of the prefix cache is being cached on that particular pod. So depending upon all this, the weighted sum of all this will be eventually be the factor for deciding from an EPP which pod the request has to route to. Now, I have one GPU. I have NVIDIA GH200 with 96 gig HBM3, and K8's implementation is basically K3s. And then I have a gateway, which is agent gateway on the llm-d side, and then I have EPP, llm-d inference scheduler. I have the model that I'm implementing here is QN 2.57 billion instruct model. I have two vLLM decode pods. So I have time sliced my GPU into four. Basically, I'm using two of those ones here. So I have two vLLM decode pods. Since it's a smaller model, 7 billion model, I can still accommodate in two pods very easily. I have four in total to test scaling, which I'll be taking videos on in future in terms of auto scaling mechanism. And both has a block size of 64. If you have a different block size from EPP configuration from what vLLM configuration is, then you will have mismatches and the index may say empty, which is one of the problems that I have seen. And then I have the 0MQ pub, which is also listening, and then also publishes the block stored from vLLM parts to the EPP. So I'm switching to my terminal. I'll show you exactly the metrics that I have. I have a script which actually checks the metrics at this point. So you can see that the prefix cache hit on each of the parts. So let me actually show, okay, get parts, show wide. So you can see my parts. I have two decode parts here, and then other parts, which is basically part of the operator, the EPP and the EPP scheduler, and then I have an inference gateway one and hotel for distributed inference event tracking. So I have two decode parts here. So you can see here, I have the logs running here. You can see from each of the parts, I have the session terminals that will show the logs in one side. And then I also have the logs from the precise scoring when I run which we can specifically see when we run the request. Now, the previous command, the previous script which I have run, the checks metrics, specifically gives against each of the pod and what are the KV cache utilization and what is my cache hit rate here. So it's evenly distributed based on the weighted metrics that I have provided in such a way that it can still get a very balanced hit rate here. So you can see that this one has a hit rate of 59%. This one has also almost similar hit rate. So my scripts here, so I have a couple of scripts. I have one, the load prefix b.sh. So what this does is like it sends 1,000 requests, same prompt again and again, 10 concurrent requests, and I will send 1,000 of those ones. And I'll see if that actually evenly distributes between the parts, and still I get the cache hit rates. And so I'm balancing the throughput and latency here in such a way that, like, I don't want one part to be overloaded. At the same time, I need to get maximum cache hits so that the recomputation doesn't need to be happened again and again, and doesn't need to be loaded into one single pod. So I ran the request here. So you can see the scorer is logging here, and you can also see the logs coming up and equally sending the request into the pods to each of these pods that we have. So now, if you look at the per pod metrics at this point, we can see that this has almost equal hits at this point, balancing it. I can again run this and we'll see this increased. I'm sending again 1,000 requests, 10 at a time. and I can see the EPP logs here. So basically here, what I'm seeing is equal request. So now I have a different prompt, and I'll send that prompt right now and see how it actually shows the prefix hit rate. So now we can see that this is a different request, and this request is again equally distributed with maximum prefix cache hit rate of 60%. And so you can still see, like, this has been increased from the previously we saw, like, this was around, the hits was around like 129,000 on the second part and 125 on this part. Now I can see 161 on this particular part and 157 on the other part. So that is how we can basically see, like, how it's been showing that distribution of workload and properly channeled across different parts. I would also like to show the Prometheus metrics here. So the Prometheus metrics actually shows us, like, how much of a cache hit rates are on each other part, and it's equal at this point, mostly across. These are two different parts that we can see, and one in green and one in yellow. One is on 59.9%. The other one is 60.2% cache hit rate. So which basically tells, we have a good cache hit rate and equally distributed across different. So the basic results are, like, the precise Prefix-Cache-Aware routing works for aggregated workload. This is an aggregated workload given the fact that it's prefill and decode on the same node. That is specifically working. And then there is the multi-signal scoring, which I did scoring in terms of prefix affinity, KV utilization, and queue depth, which is basically working, sending the request, polling the event from the KV event on each of the parts, and then sending that to EPP scheduler and intelligently routing across the parts. For our case, it's almost close to 60% of the hit rate that we have achieved, which is pretty cool, I think, especially for a testing scenario. And I'll be loading much more request and see, like, how this actually scales. I'll also have a demo on the auto scaling in the future with llm-d. Thank you so much.